Okay. So remember last time we have an issue with this problem, this Monty Hall problem. I think I missed one condition here. It is not specified clearly in the problem statement. So let's review this one. So we have 3 doors. Behind 2 doors, there are 2 ghosts and 1 door has a car. And then we can randomly pick a door. After our pick, the host will look at the other 2 doors and reveal one of the doors with a ghost. Now here's something that I need to specify more specifically. So if for the other 2 doors, if only one of them has a ghost, then that is the only one that the host can choose to reveal, right? It may happen. Supposing if you choose the ghost, then for the rest of 2 doors, one has a car, one has a ghost. The host can only choose to reveal the one with the ghost. But in the case when you happen to choose the car at the first time, then the rest of the 2 doors, both of them will have ghost behind them. So in that case, the host will randomly pick one of the doors to reveal between these 2 doors. So here there's an additional randomness. Okay. With this condition specified, I think then we can look at this calculation again. So these are all the possible outcomes for the 3 doors. Okay, the car can be in the first door, behind the second door, or behind the third door. And then we pick, let's say we pick door A, and then, yeah, let's denote the door that we pick as A, and then the host, let's assume the host reveals door B with a ghost, and apparently this B is not equal to A. And we care about this event. We care about if our choice has our choice of the door has the car behind it. So this is the event that we are interested in. In particular, we want to know what is the probability of this event conditioned on the information that the host reveals to us. So we are looking at the probability of the car is behind door A, conditioned on that the host reveals another door with the ghost. And this complementary event is the case where the car is behind door C. Okay, so we need to make a choice between A and C. And last time we showed that to calculate this one, we just follow the conditional probability rule. We can write it in this way. And this is the joint event between sigma and B. And the event sigma means that door A has the car. So in this case, we know that the 3 gifts behind the doors are cars behind A, and the other 2 ghosts are behind door B and C. So we have C, G, G as the distribution of the gifts. So this is the event sigma. Intersection with the event B, where the host reveals door B with the ghost. Then we need to calculate these 2 parts separately. So for the numerator, for this joint event, we can look at this by the Bayes rule, right? We can decompose the numerator using the conditional probability the other way around. So we're looking at the probability of B conditioned on this event multiplied by this event. This is by the conditional probability rule. And this is easy to compute. Now let's look at this term one by one. For this one, is the probability of this event. And this event means that door A has the car. And this happens with 1/3 because the car is randomly assigned to 3 doors. So the probability that door A has the car is 1/3. So that is this term. Now the first term we're looking at, given that the three gifts are distributed in this way, what is the probability that the host reveals door B with the gold? And here's the thing. So we choose the car, or we choose A, and then the other doors, both of them have golds. So the host will randomly pick a door between B and C to reveal the gold. So that's why, so basically the host has probability 1/2 to choose the door B and reveals door B with the gold. Right? So that's why we have probability 1/2 here, because the host needs to make a decision between B and C. So this gives the numerator, and for the denominator, by the Bayes rule, we can decompose this event by conditioning on three partitions of the entire omega space. Right? The entire omega space, these three outcomes naturally forms a partition. So we can decompose it using the partition lemma. And then let's look at each term. So all these marginal probabilities, they are all 1/3 because every outcome happens with equal probability. So all these three terms are 1/3. So this is clear. And what is less clear last time is these conditional terms. Now look at this one. This is conditioning on such a distribution of gifts. What is the probability that host will reveal door B with a gold? And now it's clear because the host needs to, because these two doors, the rest of two doors, both of them have golds. So the host needs to randomly pick one to reveal. And the probability that host pick door B is 1/2. And now looking at this one, in this case, door B has the car. And in this case, right, the host will always choose to reveal door C. So he will never reveal door B. So in this sense, conditional on this distribution, the probability that the host choose to reveal door B is 0. He'll never do that. And in the last case, the car is in door C, but you pick door A. So the only choice for the host to reveal is door B, right? So in this case, the host will always pick door B to reveal this gold. And that's why here we have probability 1. Okay. So if you multiply them together and sum them up, so it's 1/2. Okay. This is the denominator in this Bayes rule. And then you divide them, so you get 1/6 over 1/2, which is 1/3. So this corresponds to the probability. So given that the host reveals a door B with a gold, given this information, the probability that the car is behind door A is 1/3. Right? And on the other hand, the probability that the car is on the other door is 2/3. So this means that you should always switch to another door and change your selection. Okay. And then that finishes 1.3. So today we are going to talk about independence among multiple events. So before we introduced independence between two events, right? So if two events E1 and E2, they are independent, that means by definition, the probability of the joint event equals to the product of the probability of the individual event. This works for two events. We only need to care about Like this is the only combination of the two, right? But let's say if we have n events, we have multiple events, and we call them independent. And this is a little bit tricky. If for all subsets, you pick any subset of events, or put it the other way, you pick any number of events among all these events. For those events, they need to be independent. Right. So here you pick any subset S among these indexes, and for those subsets of events, their joint event must be independent. For that subset of events, they should be independent in this sense. So that means this holds for any two events of this among this entire set of events. You pick any two events, they should be independent. And moreover, you pick any three events, they should be independent. You pick any four events, they should be independent. Right? Up to you pick any n events, they should be independent. So this has to hold for all subsets of this set of events, not just two. Okay. So for example, if we have three events A, B, C, then in order for the three events to be called independent, we need every two of them to be independent. So this has three different combinations. And moreover, we need every three of them to be independent. Now, in this case, we only have one possible combination. So ABC equals to PA, PB, PC. So you need to verify you need to have independence for arbitrary number of events from this set of events. And we have a remark here. So pairwise independence between of all these events cannot guarantee their independence. Okay. We need, in addition to pairwise independence, we need more than that. We need every subset of the events to be independent. So this is not sufficient. And we'll have some counterexamples to show later to show that some events, they might be pairwise independent. They may be pairwise independent, but If you look at three of them together, they are not independent. They do not satisfy this one. So this pairwise independence they do not necessarily imply this independence between three of them or four of them, among three of them, four of them. And we need another definition called conditional independence. And this one is very intuitive. So A and B so conditioned on the event C, we say A and B are conditionally independent if the joint event conditioned on C equals to the product of the conditional probability of the two. So this is like you can view, because we know that this is a proper probability law. This conditional probability is a proper probability law. We have proved that when we talk about this conditional probability. So conditional independence basically means that under such a probability law, we can still talk about independence between any two events. Okay. So the only thing that we changed is the probability law. Okay, so basically, if you want to verify independence among multiple events, you have to go over all different combinations of different number of events and verify their independence. So it is not that simple. But let's look at some examples. And here is the outcome space. Each outcome generates 3 digits. And everything happens with equal probability. So P omega, where omega can be any of them, every outcome happens with 1/9. Here we have 9 terms, 9 terms. So let EK define event EK as case digit is 0, while K can be 1, 2, 3. EK means that among these 3 digits, the case digits is 0. Now, based on definition, we can write down these 3 events specifically. So E1 means that the first digit is 0. So looking at all these 9 terms, these are the outcomes where the first digit is 0. Right. So similarly, E2 is that the second digit is 0. So we're looking at these 3 terms. And E3 includes these outcomes. Right, this is just based on definition of the event. And now we can talk about, because we know every outcome happens with equal probability, we can look at, and these events are well defined, right? They are clearly defined. So we can look at the independence among these three events. So for example, to verify the independence, we need to start with pairwise independence. So let's look at, for example, the first pair could be E1 and E2. So I can look at E1, verify the independence of these two events. And I first calculate their joint probability of the joint event. Well, by taking intersection of the two, it seems that we are looking at this one only. And that's their intersection part. So this happens with probability 1/9. But on the other hand, if we look at the product of the individual events, so it should be 2. Now each event has 3 outcomes. So every outcome happens with probability 1/9. So each event has probability 1/3. It's basically 3/9, 3/9. So you get this one. And these two, they are equivalent. So we can claim that E1 and the E2 are independent. So this one is checked. And similarly, you can verify that E2 and E3 is also independent from each other, and E1 and E3, okay, they are all independent. You can check that by yourself. Follow the same procedure. But this is not sufficient to verify the independence among the 3 events. We still need to verify the joint event, the smallest joint event, the intersection of the 3 events. Okay, we need to verify the independence of the 3 events. So by taking the section of 3 events, we can see that the only common term is this one, and which is again probability 1/9. But on the other hand, we need to look at the product of their individual event, probability of their individual event. And this is actually 1/3, 1/3, 1/3. Okay, which gives 1/27. So these two are not equal to each other. Right? So this gives an example where 3 events pairwisely they are independent, but if we put them together, they are not independent. So we should say these 3 events, they are not independent. Okay? They are not independent. So from here, we can see that independence among multiple events is a very stringent condition. You have to verify any number of events, the independence among any number of the events. Another example. We have these outcomes. Again, they happen equally likely. Okay, we have eight outcomes, 3, 6, 7, 8. And they happen equally likely. Okay, so each of them happens 1/8 probability. And we look at this event, EK, well, the case digit is 1. And now we're looking at case digit is 1. So again, by this definition, you can check E1 means that the first digit is 1. So you have 4 terms that has 1 in the first digit. The last 4. At E2, you have these terms that has 1 in the second digit. E3. Okay, you only have 3 terms in the E3. Again, we have three events. And then the question is to check the independence of E1 and E2 conditioned E1 and E3 conditioned on E2. We want to check if E1 and E3 are conditionally independent given E2. Okay. Well, for this we just need to follow the definition of conditional independence. In order to verify this, we need to look at the joint event under condition on E2, and also look at the product of these two conditional probabilities. This is by the definition of conditional independence. Okay, so to compute this one, because the events are clear, they are clearly given here, so we just follow the definition of conditional probability, right? So writing down the definition of conditional probability. Oh. Right. By definition, is the joint event between this event and E2. And not because we have an intersection here, so in the intersection has this you can switch the order of intersection, does not change the result. So you can just intersect 3 of them and then divide it by the probability of the conditioning event. Well, and 3 sets are given, you can calculate their intersection. I think the common element is this one. Right? Only 1, 1, 1 is the common element. So that's the intersection, and divided by PE2. So because every outcome has equal probability to occur, so this one has 1/8 probability, and E2, probability of E2 is 4/8, okay? Because it involves 4 different outcomes. So this gives 1/4. And similarly, you can calculate these two conditional probabilities, okay, based on the definition of conditional probability. So this one is, I will skip the calculation. They are on the lecture notes. So once you take intersection of the two, you get this one, and then you need to divide it by the conditioning probability of the conditioning event. And this one is against this. Now it's this ratio. And after calculation, you can verify that both of them are 1/2. Okay. So in this case, these two are equivalent. So you can say that E1 and E3 are independent given E2. But on the other hand, let's quickly see if without this conditioning, if E1 and E3 are independent. Well, E1 happens with probability, okay. Without this conditioning, we need to look at E1 and E3. Well, the intersection between these two, I see 1, is the common part. Which is 1/8, right? But PE1 times PE3, well, PE1 is 4/8. I have 4 terms here. E3, PE3, we have 3/8. Okay. So it's 4/8 times 3/8. Well, apparently 3/16. Apparently they are not equivalent, right? So this is an example where two events, they are not independent, but conditioning on another event, they can be independent. Okay, everything is based on the definition of independence and the conditional independence. All right, so conditioning on E2, E1 and E3 have nothing to do with each other. That's what we call independence. And you can see that E1 and E3, they have something in common, right? They have the common element 1, and even for E2, E2 still involves 1, So basically, these events, they are not disjoint events. They have something in common, but given one of them, the other two could be independent. Right. So this shows that independence is not very it's not cannot be inherited that straightforwardly, right? Here, these two are not independent, but given the other one, they are independent. It may also happen that these two events are independent by themselves, but given the other one, they no longer become independent. Conditioning on the other one. I think we can check. We have another example. Okay, again, equally likely, and EK is defined as the case digit is 1. Okay, so we have E1 is contains these two, E2 contains these two, and E3. Okay, and we want to check independence between E1 and E2. Okay, let's quickly do that. So now we should be very familiar. So check this one, we just need to look at this probability. Well, E1 and E2, they only have a 110 in common. So only one term, which is 104. And PE1 times PE2 is, well, 2 terms over 4, 2 terms over 4. So it's 102, 102. Okay, so they are independent, but these two events by themselves, they are independent. And then we check the independence between these two condition on E3. Check this one. By definition, we need to look at this joint event conditioning on E3. And according to the probability law, is the intersection of the 3 over PE3. Well, the intersection of the 3, between these two, we only have 110, but E3, we don't have 110. So this is empty set. Empty set is 0. So we get 0. Right. But on the other hand, we still need to look at PE1 given E3 and PE2 given E3. Okay, so this is conditional probability. Now taking intersection between E1 and E3, I see 101 as the common element. So it's just one outcome there, which gives 1/4. And PE3 is 2/4. That gives me 1/2, which is not 0. And these two, I believe you can do the same thing. Well, E2 and E3, we still have one element in common. So it's the same thing. Right? But 0 is apparently is not equal to product of 1/2 2 times. So this means that condition on E3, the independence between E1 and E2 no longer holds, right? So this shows that we can break the independence by conditioning on another event. And the previous example shows that we can build independence by conditioning on another event. Right? So in the previous example, the two events are not independent by themselves, but conditioning on E2, they can be independent. So all these examples, every example shows a very interesting case about independence. So this means that when you talk about independence of two events, you really need to understand the context. Are you conditioning on something else, or are you just talking about the two events only? Right. So basically, independence is highly nonlinear structure. Cannot be generalized to when you condition on other events. is here. So this finishes lecture 5. And I think you can probably finish homework 3. Let me quickly look at that. But problem 3, well, this one's about conditioning. Okay, this is calculate some probabilities, and again, calculating the probabilities. Here we have conditional probability, so they are covered by lecture 5, I think. I think this is also covered. Again, conditional probability. So last one is, okay, maybe this one needs lecture 6. So I guess you can at least work on the first 3 or 4 problems. Oh, I think 4 and 5 depends on lecture 6, but you can at least work on maybe first 2 or 3 problems. So I will set up a deadline later because we haven't finished lecture 6 yet. But I think we can start it to talk about. So lecture 6 is about repeated experiments and Bernoulli experiments and some combinatorics. So we can consider a single experiment. For example, you flip a coin for once. This is a single experiment. And it has a probability space, right? These 3 elements. Set of all outcomes, the sigma algebra forms by some events, and the probability law assigned to the sigma algebra. So this describes a single experiment. And then we can consider a super experiment. Which is composed of n independent repetitions of this single experiments. Okay. So you can, for example, you can flip the coin n times, multiple times. Every time is independent from the other trials. Okay. So this n experiments, we can put them together and call it a big experiment, okay, or super experiment. So we can describe this super experiment by, again, because it's an experiment, we can still describe it by constructing 3 elements in the probability theory. Right? We need the outcome space, sigma algebra, and the probability law. But here we can actually construct them based on the 3 elements of the single experiment. So in particular, the outcome space for this super experiment because the super experiments is n repetition, independent repetitions of the single experiment. So we can simply concatenate the outcomes of all the n experiments. Right. So we can just collect the outcome space for each single experiment and concatenate them together. So mathematically, so each outcome in this super experiment is the collection of outcomes from the single experiments, the repeated single experiments. So omega 1 is outcome from experiment 1, omega 2 is from the experiment 2. So basically, each omega I is the outcome from a single experiment. Therefore, when we talk about one outcome of the super experiment, we need to look at the one realization of all these independent experiments. So this is the outcome space, which is very, very straightforward, right? We just put every individual outcomes together. And then the sigma field. Now, once we have this outcome space, we can define the events, which are basically subsets of this outcome space. And the sigma field can be formed by, again, the events is formed by the events, where each event comes from this individual experiment. Again, this is a concatenation of the events for the individual repeated experiments. And each event comes from the sigma algebra that we formed for the individual experiment. And in order to form a proper sigma algebra, we need to, in addition to this, we need to consider collecting all these possible concatenated events. And then to complete a sigma algebra, we need to consider their unions, all the possible unions and the intersections, and include them into the sigma algebra. Okay. And the probability law assigned to this sigma field is follows. You pick an event of the super experiment. Okay. It is basically the product of the probability of each individual event, because they are independent, right? They are independently repeated. So the probability of, so you can interpret this as the probability that event E1 happens in the first experiment and the event E2 happens in the second experiment, and up to the last event En happens in the last experiment. But because all these experiments are independent, so you just multiply their individual probabilities together. So basically, as long as the repeated trials are independent, we can just, when we calculate probabilities, we can just calculate them one by one and then multiply everything together. So this is a this is the repeated trials where we repeat the same experiment multiple times, right? You flip a coin 100 times. Every time, every single experiment is independent from the others, and they all look the same. They have the same outcome space. They have the same probability law. The other super experiment that we need to consider is the Bernoulli trials. Well, in the Bernoulli trials, we are talking about repeatedly independent experiments. Okay, so you flip a coin independently for n times. But here we care about the occurrence of a certain event. For example, we can look at what is the probability that you get ahead in the first 3 trials, something like that, right? So you need to look at something. We care about a single event, the occurrence of a head in this first 3 trials. Yes.
This is not like we keep looking to have just calculate a certain amount of time and get one.
Yes. Yeah, but that is also another example. Yeah. So for example, we can consider this example. So consider a repeated roll of a die. So we roll a die, failed die repeatedly, and we care about event E equals to 1, which means we see a 1 as the outcome in a single experiment. And apparently PE is 106. Well, for the rest of the probability, we have 5/6. Okay. Now, for example, we can consider the probability of having the probability of this event in the first 4 trials. Which means in your first row, you see a 1. In the second row, you did not see a 1. And in the third row, you did not see the 1. In the fourth row, you see the 1 again, right? So how do we calculate this probability? Anyone tell me that? we have 4 events assigned to each experiment, and the experiments, the repeated rows are independent. Okay, every row is independent from each other. Yes. So by independence, we just decompose the joint event as the product of the probability of the individual events. And then each of them is given here. Right? So the probability that you see the first CO1 in the first row is 1/6, and you did not see the one in the second row is 5/6, and so on. So basically, you just go over the experiments one by one and calculate the corresponding probability of the events for each individual experiment. What is the probability of observing 2 event E and 2 complement event out of 4 trials? So in the 4 trials, you observe 2E and 2E complement. Right? In part A, this is a special case. Well, here in these 4 trials, we have 2E and 2E complement. But this is just one of the possibility. You may observe 2E's in the first 2 experiments and observe 2E complements in the last 2 trials. Right? There are different possibilities. So this event contains a lot of possibilities. We can list many scenarios where we can see we have 2E and 2E complements. This is one, and there could be 2E's in the first 2 trials and 2E complements later on, or they're next to each other, and well, we can list many different possibilities. So to calculate this one, we just need to so note that each of these possibility has the same probability because they all have 2E and 2E complements. So to compute their probability, you just multiply 2 probability of E and 2 probability of E complement. So each of them has the same probability. So we just need to count how many different combinations do we have for such an event. So this is related to the combinatorics that we are going to talk about next. But for this event, we call it super event. So basically, out of 4 trials, we need to see 2E's and 2E complements. Well, I just need to choose out of these 4 positions. I just need to choose 2, and I choose 2 positions to place the event E in them, and the rest of the 2 positions will be E complement. So in total, I have this many number of combinations. And for each combination, we have the same probability because for each combination, we have 2 E's and 2 E complements. Right. So this is the probability of 2 E's, and this is the probability of seeing two E complements. Right. But this is the number of the total number of combinations that has two E's and two E complements. So it's choose two from out of 4. Okay, and in the next lecture, we are going to talk about review some, I'm not sure if you are still familiar with this, but we are going to review how to calculate combinatorics and permutations in different scenarios. We have various basic rules, basic calculation rules. And then in the homework and the exam, you will need to use these rules to compute the number of cases of interest. Right? Like for example, in this case, how many cases do we have to see 2E and 2E complements in these 4 trials? So this is a combinatorial problem. Okay, so I think I can stop here. And by the way, for the office hour, today I have an appointment that conflicts with the normal schedule, but I can stay between 1 to 3 p.m. I will be on campus, but I will be over the Zoom. Okay. Afterwards, we will still keep the office hour to be 3 to 5 p.m. So today I will be in the Zoom between 1 to 3 p.m. And if you can come a little bit earlier, that will be better. So if you want to talk about homework questions, homework 2 I think is already due. So and we can look at homework 3 if you have any questions. Okay. Thank you, everyone. I will see you at 1 o'clock.